We're still back with Matt, the muscle, the laxative, Mashad. Matt, can you read number 15?
A bowling ball traveling with constant speed hits the pins at the end of a bowling lane 16.5 meters long. The bowler hears the sound of the ball hitting the pins 2.80 seconds after the ball is released from his hands. What is the speed of the ball, assuming the speed of sound is 340 meters per second?
Nice. So let's start. What are we dealing with here? We have a bowling ball traveling down a bowling alley, 16.5 meters, and it's about to hit a couple of pins at the end. Now, the total time they give us is 2.80 seconds. But, Matt, is that the amount of time it takes for the ball to travel down and hit the pins?
No, that's actually the sound of the ball hitting the pins and coming back to the person who let go of the bowling ball.
Yes. So, this is the amount of time it takes the ball to travel down the alley, and then after it hits the pins, the sound returns at 340 meters per second to the ears of the bowler. So, what this is telling me is that first, before we can calculate the velocity of this ball, we have to be able to calculate the time that it takes for the sound to return to the bowler's ears. So, this is a two-step process, as usual, like we're used to. Let's start with this. We're solving for the velocity of the ball, and it's a constant velocity, right? What does that mean about the acceleration, Matt?
If it's a constant velocity, it means the acceleration is zero.
Yes, the acceleration of the ball is zero, and therefore we also know that the initial velocity of the ball is equal to the final velocity of the ball, which we don't know. The amount of time the ball travels is also unknown because we don't have the amount of time that the sound takes yet. The distance, delta x, of the ball is 16.5 meters. As for the speed of sound, what's the speed of sound here, Matt?
The speed of sound is 340 meters per second.
Nice. Does it have an acceleration?
The speed of sound doesn't have an acceleration either. That would also be zero.
Right. So therefore we know that the initial velocity of the sound is equal to the final velocity of the sound. And as you said, that's equal to 340 meters per second. The sound travels a distance 16.5 meters. Let's calculate the time that the sound takes to travel from the bowling pins back to the bowler's ear. I'm going to write down our kinematic equations. We have V final equals V initial plus AT. Delta x equals V initial t plus 1/2 AT squared. V final squared equals V initial squared plus 2A delta x. Remember, delta means the change in. And 4, delta x equals V final plus V initial over t, over 2 times t. Matt, which of these equations can we use to solve for the time it takes the sound to travel back to the bowler's ear?
Since we need to include delta x, could we use delta x equals v initial times time plus 1/2 times acceleration times time squared?
Yes, we can. Okay, go ahead and fill this in for me. What is delta x?
16.5 meters.
Equals?
Equals 340
We're going to call that
meters
TS.
per second.
Nice.
Times t plus 1/2 times the initial velocity, which is zero.
No, that's the acceleration.
Oh, the acceleration.
Times
times
squared.
t squared.
Perfect. This second part, because it gets multiplied by 0, is going to zero out. We can ignore it. This makes our equation 16.5 equals 340 TS. How can we solve for TS? What's the step here?
We could divide each side by 340.
Nice, let's do it. Let me know what you get.
I got 0.05 seconds.
Perfect. And that's rounded. My calculator says 0.0485, but that's a good rounding. Now, Matt, using this, how can we calculate the time that the ball takes to travel down the alley?
So we know that it takes 2.80 seconds for the person who threw the ball to hear the sound of the ball hitting the pins. So we could subtract what we just got, 0.05 seconds, from 2.80 seconds to just get the amount of time it took for the ball to hit the pins.
Right. So, really fast, 2.8 minus 0.05 means that the amount of time it takes for the ball to travel down the alley to hit the pins is going to be equal to 2.75 seconds. There we go. I'm going to replace that up at the top here, 2.75 seconds. And now we should be ready to solve for the constant velocity, the v initial and the v final, of our bowling ball. Matt, which equation should we use from our kinematic equations to solve for v initial or v final?
I think we'd be able to plug it back into number 2.
Number 2. All right, we're taking another number 2.
Good night, everybody.
We have 16.5 equals v initial is what we're solving for. The time the ball takes to travel is 16.5. I apologize. It's 2.75. That's the distance. 2.75 plus 1/2 times 0, because the acceleration is 0 still, times 2.75 squared. But this second part zeroes out because it multiplies by 0. We're finishing up here. We have 16.5 equals v naught of the ball times 2.75. How do we solve for v naught?
So to solve for v naught, we just need to divide each side by 2.75.
Perfect. Can you do that on your calculator really fast?
2,000 years later.
For that, I got 6 meters per second.
Perfect. And that is the velocity of our bowling ball. Great stuff, Matt. Hey guys, we're back today with my good friend Matt the Laxative Mashad. And today we're going to be doing a few more physics problems.
It's going to
Matt.
be a real hoot and a holler, I tell you what.
Yeah, exactly. Go ahead and read this question out loud, Matt.
You got it. So, a baseball pitcher throws a baseball with a speed of 43 meters per second. Estimate the average acceleration of the ball during the throwing motion. In throwing the baseball, the pitcher accelerates it through a displacement of about 3.5 meters from the behind the body to the point where it is released.
Awesome. So yeah, Matt, what are we actually solving for in this question? What is the unknown?
The unknown is the acceleration between the ball being pitched from the beginning of the throw to when the ball is released. So it's not the acceleration of the entire pitch, it's just during this throwing motion.
Perfect. So we're finding the acceleration. Do you know the initial velocity here?
The initial velocity is 0.
Do you know the final velocity?
The final velocity is 43 meters per second.
Nice. And what other information do they give us?
We also know that the displacement of distance of the pitch is 3.5 meters.
Awesome. Okay. Do you remember the kinematic equations?
Yes. V final equals V initial plus acceleration times time.
Nice. How about the second one?
Let's see. Delta X equals V final plus V initial divided by 2 times time.
Oh, nice. Yeah, so that's a different one. V final plus V initial over 2 times time. V final plus V initial over 2 is the average velocity. However, we're not actually going to use this one. I just don't consider it in the 3 primary kinematic equations. We'll make that a fourth down here. This one is going to be V initial times time plus 1/2 AT squared. However, we can put that one off to the side. It's not a bad one. I just don't consider it in the 3 primary kinematic equations. Delta X equals V final plus V initial over 2 times time. Do you remember the third kinematic equation?
No.
So this is going to be V final squared equals V initial squared plus 2A delta X. Now, which of these 3 equations should we be using to solve for the acceleration, given the information that we have?
I think we should use number 3.
Yeah, number 3 makes sense to me. Can you help me fill it in?
43 meters per second squared equals 0 plus 2 times
A is our unknown, right?
A is our unknown times 3.5.
Nice. All right. Now we just have to do algebra to solve for the acceleration, right?
Right.
Let's begin rearranging this. What's the first thing I can do here, Matt?
First thing we can do, can we divide each side by 2?
Yeah, we can divide each side by 2 and 3.5. So we get 43 squared over 2 times 3.5. And actually, we're ready to solve this. Go ahead, pull out your calculator, and we're going to do 43 squared divided by, open parentheses, 2 times 3.5, close parentheses. And let me know what you get for your answer.
My answer was 264.1.
That's what I got. What are the units?
Meters per second.
Meters per second squared, because it's an acceleration.
Okay.
Nice. Great stuff. How you feeling about this problem?
I feel good.
Yeah, you understand it?
Yes, I see that we had to use the equation where we only had one variable missing. We didn't have time, and the other equations had time, and it would have been a lot harder to solve this if we needed time to finish the problem.
Nice, perfect. So this problem's not too complicated. We could do it with a single equation. We had all of the variables except the unknown, which is ideal. Perfect. Great stuff. Hey, Matt, ready to start this problem? Can you read this one out loud?
A 75-meter-long train begins uniform acceleration from rest. The front of the train has a speed of 18 meters per second when it passes a railway worker who is standing 180 meters from where the front of the train started. What will be the speed of the last car as it passes the worker?
Nice. So for this problem, it seems like we have two scenarios. Matt, what is the velocity of the train in the first scenario when it's 180 meters from the worker?
It starts from rest, so I believe it would be 0.
Nice. What is the velocity right whenever the front of the train gets to the worker?
18 meters per second.
Nice, perfect. So that's scenario number 1. Scenario number 2 is what we're actually going to be solving for. So what is the initial velocity of scenario 2?
Scenario 2, I believe, would be 18 meters per second.
Perfect. Yeah. And then whenever it actually gets past the worker, the back of the train is located where the worker is. That's the velocity we're searching for, right?
Yes, because it's not when the front of the train reaches the person, when the back of the train reaches the person.
Right. In scenario number 1, what is the distance covered?
The distance covered is 180 meters.
Perfect. So that's going to be delta x, 180 meters. In scenario 2, what is delta x going to be?
Is 75 meters a factor of that?
Yes, perfect. So I drew out our two scenarios. We have scenario 1, the initial velocity 0 meters per second. Its final velocity is 18 meters per second. Scenario 2. This is what we're actually solving for, is the final velocity in scenario 2, whenever the back of the train is passing the worker. We have our scenarios. I'm going to start writing out the 3 kinematic equations. Number 1, we have v final equals v initial plus acceleration times time. 2, we have, that's a mistake, number 2 is delta x equals the initial velocity times time plus 1/2 acceleration times time squared. And the third one is the final velocity squared equals the initial velocity squared plus 2 times acceleration times the change in position. We're actually going to be working backwards on this problem. Let's talk about scenario 2 in isolation first. In scenario 2, what are we looking for?
In scenario 2, we have to figure out when the last car reaches the railway worker.
Are we looking for when? That would be a time. Specifically, what do they want?
Or do they want the final velocity of that?
Yeah, Exactly. So we're finding the final velocity. That immediately eliminates our second equation because it doesn't include the final velocity. So we're left between the first and the third equation. Let's try and figure out the information we're given. We have the initial velocity, we have the distance. We're missing acceleration and time. The first one includes acceleration and time. The second one just includes the acceleration. So I'm going to pick the third equation here because it has the least unknowns. Just acceleration is what we're looking for. We don't have that acceleration, but we know that if we had it, we could solve for the final velocity. So before I plug anything in, we're going to go to the first scenario and see if we can find the acceleration in that scenario. Do you understand why we're doing that?
Is it because we can't solve the final problem without solving for one of the variables that are still unknown to us?
Yeah, exactly. We're kind of searching for the unknown variable, which in this case is just acceleration. So in scenario one, if we are new unknown, we have to find the acceleration. Now for this one, we're given v initial, v final, and delta x. Which of our three equations includes v initial, v final, and delta x? And A. Does the first one have those four variables?
We don't have distance in there.
Right. And we do have time, which adds another unknown. So we wouldn't be able to solve for the acceleration. So it's not the first one. How about the second one?
So the second one, while we have the distance, we don't have v final.
Right. And it also has the time. So it's not the second one.
Yeah.
Does the third equation work?
Even without knowing the v final, I think it's possible to figure out the acceleration by completing problem 3.
So for the first scenario, we actually know v final.
Oh, okay.
This is tricky. The first scenario, v initial is 0 and v final is 18 meters per second. Let's use the third equation and fill it in with our first scenario. What is v final equal to in the first scenario?
18 meters per second.
Right. So we have 18 squared. What is the initial velocity equal to?
The initial velocity equals 0 because it started from rest in that scenario.
Perfect. Do we know the acceleration?
We do not know the acceleration yet.
Right, that's what we're solving for. And what is the change in position in the first scenario?
The change in position, is that 180 meters?
Yeah, perfect. Okay, let's do a little bit of algebra to solve for the acceleration, which we can then use to plug into the second scenario. Nice. So what I'm doing is 18 squared equals 2a times 180. Now, I'm just going to swap sides. I have a over here, and I divide both sides by 2 and by 180 to isolate a. So I end up with a equals 18 squared over 2 times 180. Now, when you put this into your calculator, it's important to use parentheses in the denominator to make sure that you're dividing the top by both of these and not dividing it by 2 and then multiplying it by 180. Let's take a second and calculate the acceleration. 18 squared divided by open parentheses, 2 times 180, close parentheses. Hit enter, and my answer, I get either 9/10 or 0.9 meters per second squared.
All right, I was able to get that too.
Perfect. I'm going to put a circle around that. This was our calculation for scenario number 1. Let's use the calculation for scenario number 2. And we already decided which equation we're going to use for scenario number 2, right?
Right.
Which one was it?
So we're going to use number 3.
Perfect. Okay, what is our final velocity in scenario number 2?
For scenario 2, is that what we're solving for?
Yes, that's kind of a trick question.
Okay.
So we just write it down as is. Exactly. What is our initial velocity in scenario 2?
Would that be 0.9?
No, that's the acceleration.
Oh, we have the, okay, so we can plug that in later.
Mm-hmm.
But for scenario 2, is that 180?
Yes. Well, it's okay. 18.
18, okay.
Sorry, I got that enough. So the initial velocity is 18, Maybe you had trouble seeing it. That's okay. 18, I wrote 180 because I got a little confused. 18 squared, and then plus 2, the acceleration is 0.9, right?
Oh, that's the acceleration that we just solved for. So that's
Exactly.
where it gets plugged into.
And then what is our change in position, delta x?
Delta x this time is at 75.
Yeah, perfect.
Okay.
Now, this problem doesn't take very much algebra at all. All we have to do is take the square root of both sides to get rid of that squared above the v final squared. And we end up with v final equals the square root of 18 squared plus 2 times 0.9 times 75. Be careful calculating this. Make sure that everything falls under the umbrella of that square root symbol. On a calculator, you do this with parentheses. So I'm typing in the square root, open parentheses, 18 squared plus 2 times 0.9 times 75, close parentheses. Let me know what you get for your answer, Matt.
I got 21.42.
That's what I got. And it's, what are the units?
The units for this, would they be meters per second?
Yeah, perfect, because it's a velocity. Nice. That's our final answer. That's how fast the train will be going whenever the rear of it passes the person standing there.
And this problem had 2 steps because in a less complicated problem, it would just be when the front of the train reaches the person. But we had to know how long the train was to know when the back of the train reached the person. And that's why it was a 2-scenario problem.
Yeah, exactly. We had to work our way backwards in order to get the missing piece, which was the acceleration. Good stuff.
A fugitive tries to hop on a freight train traveling at a constant speed of 5 meters per second. Just as an empty boxcar passes him, the fugitive starts from rest and accelerates at 1.4 meters per second squared to his maximum speed of 6 meters per second, which he then maintains. How long does it take him to catch up to the empty boxcar? What is the distance traveled to reach the boxcar?
Perfect. Matt, I'm going to expect that voice to maintain through this entire video.
No problem.
What are we solving for here?
So it's in 2 parts. So we're solving for time for A, and we're solving for the distance traveled for B. And we're probably going to have to solve in that order to get each answer.
Let's talk about this a little bit. Our fugitive is catching up to this train. They're starting at the same place, and the train is going at a constant 5 meters per second. The fugitive starting from rest. So initially, that train is going to get a bit of a head start, but then the fugitive is going to start accelerating until he catches up to the train. So we want to solve for the amount of time it takes for the fugitive to catch the train. Let's start with that in part A. So I've put a little drawing here. Our train is starting. It has a constant velocity, meaning v initial and v final are equal, of 5 meters per second. We can also state, but we don't have to, that its acceleration is equal to 0 meters per second squared. Now we have our fugitive starting with 0 meters per second velocity and accelerating at 1.4 meters per second squared. They're both starting at the distance is equal to 0, time is equal to 0. Let's start with our fugitive. How long is it going to take for the fugitive to get from 0 meters per second all the way up to 6 meters per second?
We're solving for time.
We are.
Do we not know that yet?
We don't know how long it takes to go from 0 to 6 meters per second for the fugitive, but we can solve it.
Could we use v final equals v initial plus acceleration times time?
Yeah, let's try
for it?
that. V final equals v initial plus at. What's the final velocity that we're considering here?
The final would be 6 meters per second.
Nice. We have 6 equals the initial 0 plus the acceleration is what?
1.4 meters per second squared.
Nice. Go ahead and solve for that time. I'm going to call this time t1 because it's the amount of time he takes to get up to speed. So this is going to be 6 divided by 1.4.
And I got, is time 4.29 seconds?
Yeah, perfect. 4.29 seconds. Let's see how far he travels in those 4.29 seconds. So now we have time, we have initial velocity, we know the acceleration. How can we calculate the fugitive's distance covered in that time?
So we know in 4.29 seconds, he is moving one, and I forget the unit, but we know the train is moving at a rate of 5 meters per second.
Oh, so what you're saying is that now he's moving 1 meter per second faster than the train.
And that's how we'll know when he's caught up, is we have to know the train is going +5, +5, +5. And then
Yeah.
he will accelerate to this rate of 6 to the point where he'll eventually catch up with them when we add this all together. So
Exactly.
it's tricky, but yeah, it's not. Yes, it's tricky.
Good call. So what we're going to do first is we're going to make sure that he hasn't caught the train by the time he's accelerated to 6 meters per second. Now, we can mostly assume this to be the case, but let's just verify it using our methods. I'm going to use the second equation, delta x equals v naught t plus 1/2 a t1 squared. This is going to give us the distance that the fugitive travels while he's accelerating, or she. I don't want to make any assumptions here. Delta x, what's the initial velocity of the fugitive?
The initial velocity of the fugitive is 0.
0. What's our time?
4.29 seconds.
Right. Doesn't really matter for this part because it gets multiplied by 0 anyway. It's plus the 1/2, 1.4, that's our acceleration, times 4.29 squared. Can you calculate the distance that the fugitive travels in this time? 0.5 times 1.4 times 4.29 squared is what I'm doing on my calculator.
I got 9.2.
I didn't get that. Could you tell me exactly what you typed in?
I put in 0.5 times. Oh, I typed it in wrong.
That's okay, that happens.
I put in 1.0 instead of 1.4. I'll try that again.
Gotcha. This is why we check. A lot of times I'll be doing problems and I'll get something wrong, and it's always just the silliest mistake.
This time I got 12.89.
That's what I get. So, 12.89 meters. Let's just verify that he hasn't caught the train by calculating how far the train traveled in that same amount of time.
Okay.
So, this is delta x for the fugitive. We're gonna do delta x for the train. Matt, what equation should we use here? Or how should we fill in our second kinematic equation to solve for the train's distance?
So we have the distance that the fugitive traveled.
Right.
And we're trying to find how far the train traveled.
Yeah.
Is it possible to do this same equation again, but then plug in what we know about the train instead of the fugitive?
Yes. Go ahead and start that. Let me know what I should plug in for V naught, V initial.
Okay, so the V initial for the train doesn't start from rest.
Mm-mm.
The train starts at the constant speed of 5 meters per second.
Perfect. And how much time are we taking for this train? We're testing it over the same amount of time, right? To see how far it travels.
Okay, so we can put the same time that we had plugged in before.
Exactly.
That would be 4.29 seconds once more.
Plus 1/2. What is the acceleration of the train?
So the train's at a constant speed. It's not accelerating.
Yes, that's huge. So notice here, constant speed means acceleration is 0. That's a trick that they're going to throw into a lot of problems that not everybody sees their first time through.
And then we put in 4.29 again, squared.
Right. And really this whole second half, we don't have to do any calculations because it just gets multiplied by 0.
Right.
Let me know how far the train travels, Matt.
Would that be 21.45 meters?
Yes. So, did they travel the same distance?
They did not.
Right. That's a good way to verify that we have to expand this problem a little bit. This is where it gets a little tricky. So, our fugitive, his total distance covered is going to be something like this. We know that from here to delta x, from starting to 6 meters per second, it's going to take him 4.29 seconds. So we have to get that the delta x of the fugitive is equal to the delta x of the train. What we're going to do for this is the delta x of our fugitive, it's going to be v initial t1 plus 1/2 a t1 squared. But then once he gets up to that speed, we're going to have a new initial velocity. We're going to call this v naught prime. And v naught prime is equal to 6 meters per second. Or in other words, it would be his v final from the previous one. And that is going to be multiplied by t2, some new time. All of this is going to be equal to the train, and the train's velocity is constant. V naught train, I guess I should call this v naught fugitive and v naught prime fugitive, times t1 plus v naught train times t2. This is pretty tricky. We can do this because this entire umbrella here falls under the distance traveled by the fugitive. First, whenever he's getting up to speed, and then when he's moving at constant speed. The second part is the train moving at constant speed for time t1, and then continue to move at that constant speed for time t2. So this falls under this umbrella of the distance traveled by the train. And we know they're going to be equal.
So this is my first exposure to v naught prime and these labels.
Yeah.
So I can't pretend that
It's tricky,
I fully
right?
understand it yet. This is my first exposure to it. Are these labels that we designate to help organize the problem? Or is this a whole new equation?
This is actually something kind of separate. You don't have to memorize these labels. This is something that I'm coming up with in order to give meaning to these variables. All I'm doing is I'm differentiating the initial V naught from the final V naught.
Oh, so this isn't a new equation. This is just something you're using to understand what each thing is when you're solving.
Exactly.
Okay.
And there are multiple ways to do this problem. I decided to put it into a giant equal equation here. We know that they have to travel the same distance. And so we know that the distance traveled by the fugitive is going to be the acceleration distance plus his constant velocity distance whenever his velocity is 6 meters per second. For the train, it's going to be the constant velocity for time t1 plus the constant velocity for time t2. So it turns out what we're solving for here is just t2. This is going to make more sense. Let's continue with the process. So the initial velocity of our fugitive is 0 when they start. T1 is 4.29 plus 1/2, 1.4 times 4.29 squared. We already kind of did that. So we know that this part's going to be 12.89 meters, right? This is what we did in part 1 here. Now we have to add 6 meters per second because that is the velocity that he gets up to, times t2. And t2 is what we're going to be solving for here. This is going to be equal to the velocity of the train, which is 5 meters per second, times t1, which is 4.29, plus the same constant velocity of the train, times t2. Now, this is a lot to look at. Immediately, I'm going to simplify it. We know that this whole section is equal to 12.89 because we solved that earlier up here, plus 6t2 equals, what was 5 times 4.29? We solved that before, right?
Oh, that is 21.45.
Plus 5t2. This is solvable, isn't it?
It is.
I'm going to start by subtracting 5t2 from both sides, and I'll subtract 12.89 from both sides. Okay, 6t2 minus 5t2. What is that going to be equal to?
1t.
Yeah, or just T2.
There we go.
6
Oh,
minus
so
5
it
is 1.
isolated it.
Yeah, we did. And this actually worked out really nicely. We don't have to do any division after this. Pull out your calculator and go ahead and do 21.45 minus 12.89. Keep in mind, these just cancel out. That's the whole point of subtracting those numbers.
8.56.
Perfect. That's what I get. 8.56. What's the unit?
8.56 meters.
It's time.
Oh, it is time. Okay. Seconds.
Seconds. There we go. Now, is this the total amount of time that it takes the fugitive to catch the train?
No.
How do we get the total amount of time?
Isn't this time just the time it took to get to the rate of 6 meters per second?
No, that was T1.
Oh, that was T1. Okay.
This is the time it takes from whenever the fugitive gets to 6 meters per second to then catching the train.
Okay.
So we can add them together. I'm going to put this in a circle because it's not the final answer. So our total time, I'll just call it T, is equal to T1 plus T2. So we have it being 4.
Oh, so T1 was 4.9.
Yeah, exactly.
Okay, so we have that.
Go ahead and calculate the total time.
That would be 12.85 seconds.
Nice. Awesome. Is this making sense?
This was one of the hardest ones, I
Yeah,
think.
not an easy question at all.
Yeah.
So, if anyone is watching this, this is not the only way that you can solve this problem. Let us know if there's another way that you could figure out how to solve this, and maybe if you can solve it easier or faster. And also, make sure to remember this kind of math next time you're trying to hop onto a moving train.
Oh, brother, where art thou? It looks like we're off to the races with a racing-themed problem. Are you all ready for this? Mary and Sally are in a foot race. When Mary is 22 meters from the finish line, she has a speed of 4 meters per second and is 5 meters per second behind Sally, who has a speed of 5 meters per second. Sally thinks she has an easy win, and so, during the remaining portion of the race, decelerates at a constant rate of 0.4 meters per second squared to the finish line. What constant acceleration does Mary now need during the remaining portion of the race if she wishes to cross the finish line side by side with Sally?
So this is kind of a tricky setup. What do they have to cross the finish line at the same of?
The same acceleration.
Not acceleration.
Same time.
Same time. Perfect. They have to cross the finish line at the same time. So what we're going to be doing here is we're going to be calculating the amount of time it takes Sally to cross the finish line. And then we can use that time and plug it in for Mary to be crossing the finish line in the same amount of time as it took Sally. Now they have different initial velocities, different accelerations, which we're going to be solving for Mary's acceleration, and they're traveling different distances. So what is our unknown for Sally, and what do we know?
What we know about Sally is she's 17 meters out from the finish line because she's 5 meters ahead of Mary.
Nice. Do we have her initial velocity?
I believe she has a speed of 5 meters per second.
Nice. What else do we have?
We know that she is decelerating at a constant rate of 0.4 meters per second squared.
Right. So I'm going to put A equals negative 0.4 meters per second squared. Perfect. Now for Mary. What are we actually trying to find with Mary?
With Mary, we have to find her constant acceleration that she'll need to finish alongside Sally.
Yeah, perfect. We have her initial velocity, right? What is it?
Her initial velocity is 4 meters per second.
Perfect. And what distance does she have to cover?
She has to cover the full 22 meters.
Awesome. So this is our setup. We have for Sally, and we're going to start with Sally, we have her initial velocity, we have her acceleration, her distance, and we want to find the amount of time it takes Sally to cross the finish line. With that time, we're going to be able to calculate Mary's acceleration. Let's start with it. What equation from the three kinematic equations should we use to calculate Sally's time?
I think we should use number 2 because the position is included in the problem.
Perfect. We have everything here. The change in position, the initial velocity, time, which is what we're searching for, and acceleration. So I'm going to go ahead and begin filling this in. We have 17 equals, what's the initial?
5.
Perfect. What's the acceleration?
The acceleration is a deceleration of negative 0.4 squared.
Perfect. Meters per second squared. And then we have to square time. This is a little frustrating because this is quadratic. So,
Yes.
quadratic, we have two things. You want to get the equation into the form ax squared plus bx plus c equals 0, and then you want to use the equation negative b plus or minus the square root of b squared minus 4ac over 2a. And this will give you two solutions for your time in this case, because time is the variable. So you replace x with t.
Okay.
Now, and I could just put actually t equals in this case. Normally it's x equals. But let's first start by getting that into the quadratic form. This top equation into quadratic form. Really fast, what is 1/2 times negative 0.4? Just think 4 divided by 2.
Would that be negative 0.2?
Exactly. Plus, or minus in this case, minus 0.2 t squared. Now I'm going to rearrange this so it's just like our first equation. I'm going to add 0.2 t squared to both sides, and I'm going to subtract 5t from both sides. I end up with this, 0.2 t squared minus 5t plus 17 equals 0. Now notice this follows our quadratic form. A x squared plus bx plus c. So what is A going to be equal to?
Would A be 0.2?
Yeah, perfect. What is B going to be equal to?
B would be 5t, or 5.
Negative 5 in this case. It's a
Okay.
little tricky. Circle that a little better. And what is C going to be equal to?
17.
Perfect. Let's create our quadratic equation. T equals, what do we put in for the first value here?
T equals negative, or would it be 5?
Exactly. Negative of negative 5 just becomes 5 plus or minus the square root of negative 5 squared, which is really just 5 squared because any negative number squared is positive, minus 4 times, what is A?
4 times 0.2,
And then what is C?
17.
Perfect. All over, we have to make sure that if we type this in, we put the entire top in parentheses. I've made that mistake before. This is all over, in parentheses, 2 times A, which is 0.2. Let's go ahead and do that calculation really fast on our calculators. And I'll do this on Google. As you can see, I've already practiced doing this the correct way. I'm just going to start with plus, and we have the square root of 5 squared. I don't have to make it negative because a negative number squared is a positive number, minus 4 times 0.2 times 17. Close parentheses inside that square root, and then close parentheses for the entire numerator. And I'm going to divide this by 2 times 0.2. Now, what we actually get, whenever we do plus here, we get 20.94 seconds. Whenever we do minus, so we get t equals 20.94 seconds. And then when we do minus, we get 4.06 seconds.
Oh, if it's plus or minus, and it's a parabola, and we always rule out one of them as the more sensible answer.
Right. In this case, let's talk about which one of these is the more sensible answer. 20.94 seconds or 4.06 seconds. So
Yeah,
here's
so
what's
you were
happening.
doing the math right. We just had to figure out which of the two was better.
Yeah, exactly.
Okay.
So what happens is Sally is running towards this finish line. And as she's going, here's the finish line. It takes her 4 seconds to cross the finish line. But it's not over there because after she crosses the finish line, our problem assumes that she's still running and she's still decelerating. So eventually, she's going to run pretty far in this direction, slow down, and then begin to come back because she's still accelerating backwards, right?
Right.
And so she's going to cross the finish line going the opposite direction after 20 seconds. Does that make sense? Literally, if I'm running and I cross the finish line after 4 seconds, but instead of stopping and being like, I'm done, I keep running, slowing down, and then I start going backwards. And then I cross the finish line backwards after 20 seconds.
Okay.
It's a little
I kinda see
weird.
that. Yeah.
But if it was a parabola, here she is moving, and then boom, 4 seconds, boom, 20 seconds. If 0 is our finish line, then she crossed it initially at 4 seconds, kept running, slowing down, crossed it again at 20. Tricky problem. So the time we're interested in using is 4.06 seconds. So Mary has to cross in 4.06 seconds. Okay, this is some very upsetting news, I know. But now we have to actually solve for what the question is asking for. We have to solve for Mary's acceleration in order to cross the finish line in 4.06 seconds.
But now we have Sally's time that we can plug into Mary's equation.
Exactly. So I'm going to draw a line here. And let's start solving for Mary. Which equation are we going to use to solve for her acceleration?
We're going to use the second one again.
Perfect, because it has delta x, initial velocity, acceleration, which is what we're looking for, and now it has time.
So it would be 22 meters equals 4 meters per second times t plus 1/2 of a times 4.06 squared.
Perfect. I'm going to simplify
when we know
this.
t, we could have done 4 times 4.06.
Exactly. And I'm going to do that really fast on my calculator. I get 16.24. And I'm going to do 1/2 times 4.06 squared. So 4.06 squared divided by 2 plus 8.24a. Can we solve for this acceleration now?
I believe so.
What's the first step for the algebra here?
Could we divide each side by 8.24?
That could work. I think the easier method is to start out by subtracting the 16.24 first.
Okay.
But we could divide both sides. It's just we had to divide 2 numbers instead of just 1.
Okay.
So let's do the minus 16.24 on both sides first. So I get 5.76 equals 8.24a. And now we're completely ready for your step.
So we divide both sides by 8.24.
Yeah, exactly. And I end up with 0.70 meters per second squared once I round. Is that what you got?
I did get that. You rounded up after 0.69.
Exactly, because I got 0.699.
Yeah, that's what I got too.
Perfect. Yeah, and that's our acceleration. So Mary has to accelerate at 0.7 meters per second squared to catch Sally, who is decelerating at 0.4 meters per second squared by the time they get to the finish line. Awesome. Any questions about this one?
I see this is another 2-step problem where we had to solve Sally to get the information we wanted from Mary.
Yeah, there's a lot going on here. Yeah, to quickly recap, we wrote down all the variables, including the variables that we were looking for. We wrote down our kinematic equations so that we had them on hand to choose from. We solved for the amount of time it took Sally to cross the finish line, and we ended up having to use the quadratic equation. And then we plugged in that time to solve for Mary's required acceleration. Awesome stuff, Matt. All right.
A stone is dropped from the top of a cliff. It is seen to hit the ground below after 3.55 seconds. How high is the cliff?
Okay, what do we know here?
We know that the initial velocity would be 0 because it's being dropped from a place.
Right?
And we also know that the force of gravity is acting on it, and that would be negative 9.8.
Nice. And we know that the time is 3.55 seconds.
Yeah.
We are looking for delta x, the change in position, or the change in height. If you want to call this delta y, that's also an option. What equation can we use that's going to help us solve for delta y using these other variables?
So we could use delta y equals initial velocity times time plus 1/2 times acceleration times time squared.
Nice. Let's go ahead and fill this in. Delta y, what's the initial velocity?
0.
And the time's 3.55, but I'm not even going to put that because anything times 0 is 0, plus 1/2 times negative 9.8 times 3.55 squared. Can we solve this on our calculators?
We can.
Let's do it. I'm not going to even include the 0 times 3.55 because I don't need to. I'm going to do 1/2 times negative 9.8 times 3.55 squared. Now, if you come up with an error when you're doing that, make sure that there's usually a negative button and a minus button, and those are two different things on your calculator. Matt, what did you get for your answer here?
I got negative 61.75 meters.
This is the distance that the rock falls. Now let's note here, the final, y final is going to be the bottom. It's going to be equal to 0 meters. Y initial is the top. We have delta y equals y final minus y initial. So if we want to get y initial, we just solve like this. Negative 61.75, that's delta y, equals 0 minus y initial. And we get that y initial is 61.75 meters as the initial position. Position versus distance. Similar, but different things.
Pardon me.
Bless you. Awesome. Let's go on to part 2, or number 40, I should say. This is a completely different question. It has nothing to do with number 39. Go ahead and read this one, Matt.
Estimate how long it took King Kong to fall straight down from the top of the Empire State Building, 380 meters high, and his velocity just before landing.
Awesome. I tried drawing the Empire State Building and I failed miserably, so I'm drawing a rectangle. So we have that delta y is 380 meters. We want to calculate time and final velocity.
Could we use delta y equals initial velocity times time plus 1/2 of at squared and solve for the missing variable that way?
Let's try it. What is the acceleration going to be equal to?
Negative 9.8.
Perfect. What is the initial velocity equal to?
0 once more.
Perfect, because he's falling, and so he didn't jump down or jump up at the beginning. And we want to find time. Go ahead and plug these in to solve. So we get negative 380 equals 0 times time. That cancels out. Plus 1/2 times negative 9.8 times t, which is what we're solving for, squared. I'm going to do a little bit of algebra. This just goes away. We don't have to worry about it. Negative 380. Multiply both sides by 2 to get rid of that 1/2. And divide both sides by negative 9.8. Not 9.t. 9.8. That's going to be equal to t squared. If we want to solve for just t, we take the square root of all of that. 380 times 2 over 9.8. Notice I got rid of the negatives because a negative over a negative is a positive. If you put this in your calculator, make sure it's all in parentheses inside the square root. Matt, let me know what you got for this answer.
I got 8.8.
Nice. What's the unit?
The unit is 8.8 seconds.
Awesome. That is our time. Now the second part is asking for the velocity just before landing. So we have a second unknown, v final, but now we know our time.
What I think we can do here is we could use v final equals v initial plus acceleration times time now that we've solved for the missing time variable.
I agree. Let's go ahead and use this to solve. V final equals 0 minus 9.8 times 8.8. Let me know what you get.
Would it be negative 86.24 meters per second?
Yeah, awesome. Our final velocity is going to be going down at 86.24 meters per second. Good stuff. Do one of those virtual high fives through the camera.
A kangaroo jumps straight up to a vertical height of 1.45 meters. How long was it in the air before returning to Earth?
This one's pretty straightforward. What do we know about this kangaroo and what do we want to find?
We know that starting from a resting position, it reached a vertical height of 1.45 meters. I have a feeling that even though they don't give it to us in the problem, we could use gravity to help solve it.
Yes, we know that the acceleration is equal to gravity, which is negative 9.8 meters per second squared. Also, you said it started from a resting position, but that's not technically true. It had to start with an initial velocity, right? In order to be moving up.
Okay, so, we want to know how long it was in the air.
Right,
So
we want to find the time.
1.45 the initial?
1.45 is the height it makes it to. We can consider the initial position to be 0. So we have a few things so far. I'm just writing them down casually here. We're looking for the time it's in the air. We know that the change in vertical position, I put delta y to represent vertical instead of delta x, is equal to 1.45 meters. We have that the acceleration is negative 9.8 meters per second. Let's talk really fast about initial velocity and final velocity. This is kind of tricky. So we have our kangaroo on the ground and it's about to leap up in the air. So once it goes, its initial velocity is going to be somewhat significant. But whenever it's actually up in the air, it stops, right, momentarily. So when it's actually at the top, we can consider this to be its final velocity if we want to. Now, if you throw a ball up in the air, at the very top of the trajectory, what is its velocity going to be? At the bottom, it has some initial velocity. But at the top, for a split second, its velocity is 0, right? Because if it's only moving vertically, then at the very top, it had to stop and then start moving back down. So our initial velocity is unknown, but at the top, we can actually know that the final velocity is 0 because it's turning around. So I'm going to put that in here. We actually can put that v naught, the initial, is unknown. Now keep in mind, if we use this as our equation, then we're going to get that the amount of time we calculate is only the amount of time that it takes the kangaroo to go from the bottom of the jump to the top of the jump. Then we'd have to double that time in order to get the amount of time it takes to fall back down to its original jumping position.
So whatever we solve for time, we have to multiply by 2.
Yes, exactly. Perfect. Let me write down the kinematic equations. V final equals V initial plus AT, not equals AT. Delta, I'll put delta y here since we're dealing with the vertical direction. Those are always interchangeable. Delta y equals V initial times time plus 1/2 AT squared, and V final squared equals V initial squared plus 2a delta x. I'll even include the fourth. This one we have delta y equals V final plus V initial over 2 times time. Which equation should we use here to calculate the amount of time it takes the kangaroo to go from the bottom to the top?
Could we use v final equals v initial plus acceleration times time?
Let's see. What is v final?
V final is 0.
Nice. What is v initial?
We don't know v initial.
Right. What is a?
A is negative 9.8.
And what is t?
We're solving for t.
Right. So since we have two unknowns, we can't actually use this one, can we?
No.
Let's try for the next one. What's the next one you want to try out?
Could we try number 3?
So, does number 3 have time in it?
It doesn't, but could we use it to solve for v initial?
Actually, yeah, that's not a bad idea. We could use it to solve for v initial. Let's do that. So we have v final is 0 squared equals v initial, that's what we're solving for, plus 2 times negative 9.8, and then delta x is, or delta y in this case, I should replace that here, just for the sake of this equation, is going to be 1.45. Now it's just a matter of doing the algebra. Let's simplify this first. We have the 0 goes away, so I'm going to do v naught squared. Basically, I'll subtract all of this to the other side. So we did it minus all of this here, minus 2 times negative 9.8 times 1.45 on both sides, and we end up with v naught squared equals, a negative of a negative is a positive, 2 times 9.8 times 1.45. Finally, all we have to do is take the square root of both sides, and we get v initial is equal to the square root of 2 times 9.8 times 1.45. Go ahead and punch that in. Let me know what you get.
I got 5.33.
That's what I get. Perfect. What are the units?
The units are, is it meters per second?
Yeah, awesome. I'm going to circle that, and I'm going to take out how I crossed out the first equation, because maybe now we can use it now that we have the initial velocity. So now, what are we going to use to calculate time now that our initial velocity is known?
Could we use number 1 now? Because time would be the only thing we don't know.
Yeah, absolutely. Can you set it up for me?
V final equals 0. So it's 0 equals 5.33 meters per second plus negative 9.8 meters per second squared times t.
Awesome. Let's solve for time.
So we want to get time on its own. Do we want to subtract 5.33 and negative 9.8 to the other side? Or is there a better way to do that?
You're right. We just subtract 5.33 to the other side.
Okay.
So we get negative 5.33 equals negative 9.8t.
Okay.
Now, the negative 9.8 is attached to t by multiplication.
So we have to divide that.
Yes, exactly. We move it to the other side by division. And that should give us our solution. Let me know what you get for the time. Remember, a negative divided by a negative is a positive. I know you know that.
So I got 0.54.
Perfect. What's the unit?
Is that seconds?
Yes. Now, did we solve the entire question, or do we have one more step? What did that time, what was that the actual time of?
We have to multiply it by 2 because what comes up must come down.
Yeah, perfect. Let's do it. So I circle anything that's not the final answer, and the final answer, I'll call this time total is equal to t times 2, because exactly what you said, what comes up must come down. Let me know what you get.
I got 1.08 seconds.
Perfect. And I'm going to round it to 1.09 because I got 1.087. Perfect. Yeah, great stuff. Is this making sense?
Yes.
Awesome.
I saw that we could solve for one part of the equation to use another equation to solve for time.
Yeah, that was good. You caught on to it before I did. I was feeling lazy and not really looking for that. But that was a great way to solve the problem. And great stuff today. I feel like really no errors on this. No mistakes. So yeah, awesome.
Suppose you adjust your garden hose nozzle for a fast stream of water. You point the nozzle vertically upward at the height of 1.8 meters above the ground. When you quickly turn off the nozzle, you hear the water striking the ground next to you for another 2.5 seconds. What is the water speed as it leaves the nozzle?
So, what are we looking for here specifically?
We're looking for the initial velocity of the water leaving the nozzle of the hose.
Right, and what are we given?
We are given the height of where the hose is above the ground, where the
Right.
water will leave from. We hear the water striking the ground next to us for another 2.5 seconds. So I think that's like the initial contact of the water after it's gone up and down and hitting the ground, and also for how long it continues to fall there, showing like how much water was let out of the hose.
Right, agreed. So, we're looking for the initial velocity we're given. We know that acceleration is negative 9.8 meters per second squared, right? Because it always is in the air.
Oh, so yes, we have the force of gravity as a number we can work with.
Perfect. Why not? I'm calling it why not because it's the initial height
Why not?
is 1.8 meters. Y final is 0 meters, and our time is 2.5 seconds. Now, can you think of which kinematic equation is going to help us solve for this? I'll write them all down. V final equals V initial plus AT, making this one delta Y since it's vertical. It's the same as delta X equals V naught T plus 1/2 AT squared. V final squared equals V initial squared plus 2A delta Y, and delta Y equals V final plus V initial over 2 times time.
Wouldn't V final equals V initial plus AT be the right way to go?
It's pretty good. Do you want to try it out?
Sure.
Okay, so we have V final equals V initial plus AT. How should I start filling this in?
Start with 0,
0 for what?
V final.
Is V final actually 0? V final is going to be the velocity as it hits the ground.
Oh no, okay.
So we don't actually know V final. However, you're thinking of V final at the very top, which is a good thought. But we don't know the amount of time it takes to get to the top. So we don't actually know V final at the bottom here. Let's try a different one maybe.
So all these contain V final and V initial.
Not all of them. There's one that doesn't contain V final.
Oh, is that number 2?
Number 2, exactly. So we have delta Y, and I'm going to rewrite delta Y as Y final minus Y initial, because that's what delta Y means, equals V naught T plus 1/2 AT squared. And yeah, let's begin to fill this in. We have that Y final is 0, Y initial is 1.8. We're solving for V initial. We know that time is 2.5. We have negative 9.8, and then 2.5 squared. Oh, it was a real close cutoff there. Let's begin to simplify this. What's 0 minus 1.8?
Negative 1.8.
Nice. And then we have 2.5 V naught plus, and then I'm going to actually do minus here. What is 1/2 times 9.8 times 2.5 squared? It's definitely a calculator question.
So I got rounded negative 30.63.
Perfect. Now, how should we do the algebra from here? What's my next step?
From here, could we divide each side by 2.5?
We could, but we'd have to divide 1.8, 30.63, and this by 2.5. So I think if first we add 30.63 to both sides, it's going to simplify things a lot more. Well, actually, let's do your way, just to make sure that people know that they can do it. Because it is an option. It's technically correct.
Sometimes my genius it's almost frightening.
So we're dividing both sides by 2.5. So on the left side, we have negative 1.8 divided by 2.5, and we get negative 0.72 equals 2.5 V naught divided by 2.5 is just V naught. And then 30.63 divided by 2.5, we'd have minus 12.25.
We could add 12.25 to the other side.
Perfect.
And then we would get our answer that way.
Yes. Let me know what you get for the final answer.
I got 11.53.
Yeah, nice. Same here. Great stuff. Yeah, that's it for this one.
So I'm just curious, did we solve the problem, or did we solve a part of the problem that we can plug in to solve another part of it?
We actually solved the problem. What is the water speed as it leaves the nozzle?
Oh, so we had enough to go off of for that then.
Yeah. So this problem is level 2 difficulty, and we're used to doing a lot of level 3 difficulty problems.
Oh, I see. So we took the bull by the horns then.
Exactly.
Okay.
Couldn't have said it better myself. Good stuff. Are you ready to do a physics problem?
I was born ready.
I thought so. I looked at that face and I thought, this guy can't wait to do some physics today. Okay, can you read number 53?
A falling stone takes 0.31 seconds to travel past a window 2.2 meters tall. From what height above the top of the window did the stone fall?
Okay, what are we looking for here?
We're looking for the distance, or the total distance the stone fell from.
Right. The distance it falls before reaching the top of the window. So, delta x is unknown, and it's what we're solving for. Some people would call this delta y because it's a vertical distance. What do we know before it reaches the window?
We know how tall the window is and how long it took for the stone to fall to the bottom of the window, I believe, from where it was dropped, which might be even higher than the window is. And that took 0.31 seconds.
Right. So that's actually a second portion of things. We're going to call that delta x of the window is going to be negative 2.2 meters because it's falling 2.2 meters. We're going to say that the time is equal to 0.31 seconds. And I'm actually splitting this into two categories. So the first category is above the window. This is before it reaches the window. And keep in mind, we need to include this because we're trying to solve for the distance it falls before reaching the window. Whenever they first let go of it, the velocity initial is going to be equal to 0 because at vertical velocity, it just started to fall. The final velocity, we're going to consider this to be whenever it reaches the top of the window, and it's unknown. Similarly, that can be the initial velocity whenever it's passing the window. It's unknown. So these two are equal. The final velocity above the window, whenever it reaches the top of the window, is equal to the initial velocity as it's passing the window. Does that make sense?
Yes, I believe you told me when something's falling, it doesn't just keep increasing speed. It hits a certain speed and sticks with that consistent speed until it hits the ground.
That is true, but that doesn't apply here. The reason is that applies whenever something's falling and there's air resistance. And usually in reality, that's always the case. There's always air resistance. But in physics problems, we don't have air resistance for some reason or another in the majority of these kinematics problems.
Oh, so just for the sake of the problem, it's telling us that it's going to hit that consistent speed once it gets to the top of the window. It's just convenient for solving the problem that way.
Yes, exactly. So here's our window. And before the window, you drop it, and V initial is equal to 0. Now, as it falls above the window, we stop it at this height. And at this height, V final is unknown. Then we would start the second portion of things. The second portion, V final, is going to be considered V initial of the second portion. It's also unknown, but these two are equal because they happen at the same point at the top of the window. So above the window, V initial is 0. We actually don't even know the time that it's falling, right? We definitely don't know delta x. That's what we're solving for. The height it falls before reaching the window.
Yeah,
The
we
one-
only know the time for passing the window itself, not above it.
Exactly. But the constant we do know is that the acceleration is negative 9.8 meters per second squared, because that's gravity, and it's in free fall. We can actually put that for both of them. But first, let's put that v final, as it's passing the window, is also unknown. And then acceleration for both of them is negative 9.8 meters per second squared. So acceleration is a constant. It's falling. Gravity's always negative 9.8. Above the window, delta x is what we're solving for. It's the height it falls before reaching the top of the window. V initial is 0 because we drop it from rest. V final is unknown, and it is going to be equal to the V initial as it's passing the window. The height of the window, delta x, is 2.2 meters. We have that here. The time it takes to pass the window is 0.31 seconds. That's the amount of time it takes to fall past the window. And so I'm looking at this. Can we solve directly for delta x, the distance it falls from above the window, with the information that we have in this left side here?
I think if we can calculate with the force of gravity, we might be able to find it from that.
Maybe. Let's try and think about it. So we can't use the first kinematic equation, right? Because it doesn't include delta x.
No.
The second one's an option. What is missing here? We're missing delta x, of course. Are we missing anything else?
We're also missing time.
We're missing time. That's a big one. Yeah, so we have two unknowns. We have to think, is it possible to get the amount of time it falls in the first part using the second portion?
Oh, like using equation 2 for the passing window part of the problem?
Maybe. See, I don't think there's a correlation between the passing window problem and the time it takes to reach the window. I think it's possible to calculate it, but it seems kind of difficult, honestly. Let's really fast look at number 3. V final squared equals V initial squared plus 2a delta x. What unknowns do we have in this question?
We don't know the final velocity.
Right?
We don't know delta x.
Yes, those are the main two. For the above the window portion, we don't know final velocity and we don't know delta x. However, what can we solve for in the passing window portion that will give us the final velocity above the window?
Let's see. Well, we have delta x and we have the acceleration.
Remember, what is equal to the final velocity above the window in the passing window portion?
Is it equal to v initial?
Yeah, exactly. If we can calculate v initial for the passing window portion, then we already have v final for the above window portion. And then we can use that and plug it into equation 3. That's tricky. Let's go ahead and do it. Let's solve for v initial in the passing window portion, or let's try to. Which equation could we use to solve for v initial on this side of things?
Could we use number 3?
Number 3. Let's see. So v final squared. Do we have v final here?
No.
No. Do we have v initial?
No.
No, that's what we're solving for. So that's two unknowns. So there's a better equation here that we could use in which we're only solving for v initial.
Could we use number 2?
Let's try it. Delta x, we have that. V initial is what we're looking for. We have the time, we have the acceleration, and again, we have the time. So yeah, that one can work. I'm going to scroll down a little bit here, and we're going to be using this passing window portion to solve. So I'm going to set up our second equation. We have delta x equals v initial t plus 1/2 at squared. Do you want to do the algebra first, or do you want to plug in the numbers first?
I want to plug in the numbers first.
Let's do it. What is delta x? Negative 2.2. Negative 2.2 meters equals v naught is unknown. What is our time?
Our time is 0.31 seconds.
Nice. Plus 1/2. What is acceleration?
Negative 9.8 meters per second squared.
Perfect. And then again, our time is 0.31 squared. Okay, let's begin to solve this. Negative 2.2 equals 0.31 V naught. You can just rearrange those. Plus, can you do 1/2 times negative 9.8 times 0.31 squared on your calculator?
I guess I won't know until I do it.
I'm gonna do the same. You're like,
Oh, I thought that was like a rhetorical question. Like, is this even possible? And I'm like, oh, I don't.
I thought you were just saying, regretfully, I can.
Okay, I got a syntax error.
Oh, can you tell me what you typed in?
I did type in 0.5 for 1/2.
That's fine. Whenever you did, don't worry about the negative. You don't have to do that.
All right, so I have 4.9 because I withheld the negative, but it should be negative 0.9. I just have to remember that.
That's fine, yeah, we can put that at the end.
Okay.
And then times 0.31 squared.
My answer was negative 0.47.
Perfect. And we know it's negative, so we make it minus that. Now, what we're going to do is we're going to add this to both sides. So add the 0.47 to both sides, and we have to do negative 2.2 plus 0.47.
So I got 2.67 on the left side.
Close. Remember, it's negative 2.2.
Oh.
So this time we do have to be careful with that. And you can do it two ways. You can either do 0.47 minus 2.2, or if you know where the negative button is on your calculator, you can do negative 2.2 plus 0.47. The reason you got a syntax error before is because you put the minus sign.
I got negative 1.26 instead now.
Not what I got. I got negative 1.73. Could you tell me what you typed in?
Negative 2.2 plus 0.47.
So you have to be careful that you don't put the minus sign. The minus sign is going to take from the previous answer. Calculator stuff is tricky.
So I got 2.67 again without putting the minus signs in.
So at the very beginning, could I see your calculator really fast?
Yeah.
Got it. And bring it up a little bit on the screen so I can see the bottom of the calculator. There you go. Do you see next to, at the very bottom, it's one of the white buttons. There's a minus inside of parentheses.
Oh, am I supposed to be using that for the negatives?
That's what you use for negative numbers. If you use the minus sign, it's a different concept. But that means negative 2.2.
Now I got negative 1.73.
There you go. Do you understand the difference between the negative sign and the minus sign?
Yeah, I do know.
Okay, perfect. Yeah, this stuff's kind of tricky. Let's keep going. That's important. Calculator stuff is not easy. Finally, we had to divide both sides by 0.31. So we get V naught equals negative 1.73 divided by 0.31. Go ahead and do that on a calculator. And you can use the negative sign now.
This one I got negative 5.58.
Perfect. Meters per second, right?
Yeah.
So I'm going to go back up to the top. We have negative 5.58. I'm going to put that in for V naught. And we can put it in for V final for the above window portion because they're equal. Now we're ready to solve for delta x above the window. Let's do it. I'm going to take this portion here and put it off to the side. But let's squeeze that over here. I should probably be doing a lot more of this in general. And let's get this last little portion too. Okay. Now, what should we be using now that we have V final to solve for delta x in the above window portion of things?
Could we use negative 5.58?
Yeah, we can use that. Which equation should we plug it into to help us solve for delta x?
Actually, would number 1 work?
Close. What is number 1 missing?
It's missing delta x.
Right, so we can't solve for it if we're missing it there. So number 1 is out for that reason.
Is it 2 again?
I'm going to have you analyze number 2 for me and tell me if we can use number 2. So for example, say delta x, that's what we're solving for. V naught. Do we have V naught?
We do.
Nice. T.
Oh, I guess V final isn't part of the problem.
That's not a big deal as long as we have everything else.
Okay.
Do we have T?
We don't have T.
We don't have T. That's why we can't do it.
So I guess it has to be 3.
Yeah, but I want you to analyze number 3. So You had to say V final. Do we have that?
We do have that.
Okay, keep going.
And then we have our V initial. We have A as well, the force of gravity. Then we don't have delta X, but we do have everything else.
Right, and delta X is what we're solving for.
Yeah.
Perfect. Nice. That's the exact process that we have to use whenever we're solving these. We just say we're only missing the one that we want. Okay, so V final squared. Actually, let's just go ahead and plug these in. For this one, I'm going to take a different approach. We're going to do the algebra first. V final squared equals V initial squared plus 2a delta x. We want delta x. And so I'm going to do the algebra to get it alone, and then we're going to plug in our numbers. What do you think is the first thing I should do to get delta x alone?
Is it possible to divide by delta X?
It could be, but that's not getting delta x alone. We want to get rid of everything else on the same side as delta x.
So is it better to subtract or divide those and put them on the side of V final?
Exactly. And whenever we're doing algebra, we want to work in reverse order of operations. So normally you would do multiplication and division first, but with algebra, we're going to do subtraction and addition first.
So could you subtract V initial from one side or each side?
We're subtracting V naught squared from both sides. So V final squared minus V naught squared equals 2a delta x. What's the next step?
Can we divide by 2a?
Yeah, perfect. And that's it. We literally get delta x, I'm just flipping sides here, equals V final squared minus V initial squared over 2a. Could put a circle around that. We just solved for delta x without any numbers necessary. But now we're going to plug in numbers.
Okay, so we know that V final is, it's still negative 5.58.
Exactly. We're just using all the information in this left column. So it's negative 5.58. We put that inside of parentheses and we square it, which is essentially going to make the negative not matter because a negative squared is a positive. What is V initial?
V initial is 0.
Perfect. And then what is A?
Negative 9.8.
Awesome. Can we solve this on our calculator?
I believe so.
I'm typing in open parentheses, negative 5.58 squared divided by open parentheses. Oh, wait, sorry. It's open parentheses, negative 5.58 close parentheses squared divided by open parentheses 2 times 9.8 close parentheses.
I got 1.59.
That's what I got.
And
it should be negative 1.59. I should have put negative 9.8 in the denominator there.
And this is, I forget the units of distance. Was it meters?
Yes, perfect. Awesome. Another tough problem, right?
Yes, another two-stepper.
Yeah, this one's a lot going on. But yeah, great stuff, Matt. And we're back with Matt the Muscle Mashad. Matt, can you read number 55 up to part A?
Figure 2 through 42 shows the velocity of a train as a function of time. At what time was its velocity greatest?
Okay, so this is a velocity versus time graph. How do you determine the maximum velocity?
Is it the x-axis, where it goes up like this? You could see the highest point in the green line.
Yeah, what time does that approximately occur at?
I would say about 48 to 49 seconds.
Yeah, good stuff. So this one's pretty straightforward. You literally just look for the highest points on the graph because it's a velocity versus time graph. Part B, during what periods, if any, was the velocity constant?
I would say from about 89 to 108.
Yeah, good stuff, because it's a completely flat line, right?
Yeah, flat line there.
Nice. During what periods, if any, was the acceleration constant?
It looks like the acceleration was constant from about 0 to 47.
Yeah, any other times?
It's possible that the deceleration was constant from about 52 to 77. but the line is a little more curved there. I wonder, it doesn't look as flat. Do you think that would still be a constant deceleration?
That's a pretty good answer. So that's the key here. We're looking for any time that we have a completely flat slope. Acceleration is represented by curvature, right?
Yes.
Yeah, perfect. And so any time that it is a flat slope, we're going to be having a constant acceleration. From 0 to about 40 seconds, it would be positive acceleration. And yeah, from maybe like something around like, I think it's pretty flat from about 70 to 77. You know, there's no curvature there. So we can consider that to be a constant negative slope. There's one more period of time where things seem to be pretty flat. What is that?
Well, I would say 90 to 108, but that's at a constant. So it's not accelerating or deaccelerating.
Yeah, exactly. The acceleration would be 0, right?
Yeah.
Right, and that is considered a constant acceleration because it stays at 0 during that time. When was the magnitude of the acceleration greatest?
Would that have been from about 108 to 121?
That would be a pretty good consideration there. What we're looking for here is whenever the slope or the magnitude of the slope is greatest.
Oh, so the highest point.
Not the highest point, the greatest slope. So whenever it's like this, that's the least magnitude of acceleration. Whenever it's like this or like this, we have the greatest magnitude of acceleration. Magnitude means absolute value, so it doesn't matter if that slope is positive or negative as long as it's steep.
Okay, would that be about 89 or 90 then?
Definitely not 90, because at 90 it's flat.
Okay, so like 88?
I would actually say probably at about 70. 70 is where it's the steepest.
Okay.
Do you see what I mean by that? We're not looking for the greatest curve, we're looking for the greatest slope, the rise over the run. So, for example, we know that at approximately 50 seconds, the acceleration is close to 0. Because if we drew a tangent line across that slope, it would be pretty flat. Then it starts to dip down, and once it gets to about 70, maybe a little past 70, it's very steep in the downward direction. That means that we have a negative acceleration of high magnitude. So, for example, if at 50, it is 0, and then at 60, it's like -1, and at 70, it could be like -1.5, and then it starts to ease back to being flat. Those are all approximations, by the way. I'm not doing actual calculations here.
Okay.
So the other contender could be around maybe 110, where that slope is again pretty steep. Now it's in the positive direction, but we don't care about positive or negative because we're looking for the magnitude. So we're just looking for the steepest slope.
Okay, so the angle is
Yes.
the best place to start. The angle of the slope.
Exactly. And that's why it's not from 0 to 40, because from 0 to 40, it's just not as steep as it is around 70 seconds.
That makes sense.
Awesome.
Two students are asked to find the height of a particular building using a barometer. Okay, they're confused, but they got the spirit. Instead of using the barometer as an altitude measuring device, they take it to the roof of the building and drop it off, timing its fall.
The Weather Service reports that barometers are falling sharply. Oh no!
One student reports a fall time of 2 seconds and the other 2.3 seconds. What percentage of difference does the 0.3 seconds make for the estimates of the building's height?
Yeah, no, I don't think they're confused. I think they know how to use a barometer properly.
You know, I think these students are like me before I met you. I'm feeling a kinship.
Yeah. Barometers are meant to measure pressure, by the way. So it would have been a struggle to measure the height of the building with pressure anyway. Doable, but pretty tough.
And I see that the barometer just kind of throws us off. They could have dropped anything to make this claim or prove this. It could have been a basketball, a package of vanilla wafers, you know, but they chose a barometer because we're going to think about air pressure while reading the problem.
2 students are asked to find the height of a particular building using a measuring tape. They decide to drop it off.
It's that number 78.
All right, let's get into this. What do we have? What's known?
So each student recorded a different time when the same item was dropped once.
Yes. So we have building and same building. And for this one, the time it took to fall was 2 seconds. And for this one, the time it took to fall was 2.3 seconds. Correct me if I'm wrong. That seems correct. That seems to be all the information they've given us. But what else can we conclude, given that we know certain things about how things fall?
So we could work gravity into it.
Right. Gravity equals, let's put 9.8 meters per second squared. Do we know anything about the initial vertical velocity?
That would be 0 to start.
Yes. V naught vertical equals 0 meters per second. Perfect. Do you think we can solve for the distance it falls from here? I'll write down our kinematic equations. Number 1, V final equals V initial plus AT. Delta x equals V naught t plus 1/2 AT squared. And delta x can always be replaced with delta y. V final squared equals V initial squared plus 2a delta x. The last one is average velocity.
Would we use number 2, delta x equals initial velocity times time plus 1/2 of acceleration times time squared?
Let's try it. Let's do it for the first one. So we're actually trying to solve for the height it falls, so delta x is just fine here. What is the initial velocity?
The initial velocity is 0.
Perfect. So I won't include that velocity times time. What's the
Because
acceleration?
that'll just cancel out.
Exactly.
Then we would have 1/2 times. Will we do negative 9.8 or can we just do 9.8?
We could just do 9.8. We know that it's going to be falling down. So if we want, we can consider the down direction to be positive here. And that can work out. Let's go ahead and plug this into our calculators. 1/2 times 9.8 times 2 squared.
For that, I got negative 19.6.
Perfect. 19.6 meters would be the height of the building, according to this person's drop. Now, we have the second one. It's going to be really similar, but instead of the 2 squared, we're going to replace it with 2.3 squared. Let me know what you get for this one.
For this one, I got negative 25.92 meters.
Nice. 25.9 meters. Okay, that was pretty easy. Now, what are they actually asking for?
What percent difference does the 0.3 seconds make for the estimates of the building's height? So we have 2 different heights here. Could we subtract from each other?
Yeah.
To find that difference?
Absolutely. So we have 25.9 minus 19.6, and we want percent difference. So I'm going to divide this by 19.6.
But you're going to divide it, not subtract?
Well, no, we do both. So we subtract it to get the difference, and to get the percent difference, we divide it by one of the values.
So when I subtracted, I got 6.3.
Perfect.
So then after that step, you want me to divide 6.3 by each one individually, or just one of them in particular?
Just one of them for now. We can say that it's the percent difference from, we'll call this the original height. The 2 seconds could be the original.
When I divided by 19.6, I got 0.3%.
Nice. I got the same thing. So because I got 0.32, I'm going to call that a 32% difference. Because to get a percentage, you multiply 0.32 by 100. And I just misspoke difference and misspelled it. Making sense?
Don't feel bad. These kids dropped a barometer off of a roof.
That's true.
We're all just doing our best.
To be fair, it's probably an easier way of getting the height than it would be to measure the pressure from the ground and at the top of the building. Because the pressure difference wouldn't be that great.
That's true.
So I don't know. Those kids had that was a high IQ move, assuming that the difference in time of the barometer falling wasn't because the first time it fell, it completely shattered, and the second time they were really dropping pieces of barometer that floated down.
And it's
So
interesting, they dropped the same thing from the same height, and there was a 32% difference.
That's
I'm
a
wondering,
huge
like,
difference.
did one student like drop it with his hand held high, and the other person dropped it from like the top of the building, but not any higher? Like, I'm wondering if that was the
Maybe
margin for error.
maybe one kid chucked it down. Let's look what a barometer looks like to see if these kids should have been dropping a barometer at all. So they look like they tend to be glass.
And it's funny, when I was picturing a barometer, I think I was picturing a metronome, like a triangular structure that would like tick and talk. So
Here's what
clearly
I'm
we all
thinking.
have a lot to learn.
I'm thinking the first student dropped it off, and the second student went down with a dustpan and gathered the bits and kind of floated these off, and they kind of sprinkled down to the ground and took a lot longer.
Wait a minute. They only came to the building with one barometer. So that's exactly what happened. If there were two drops, then the second drop would have just been pieces.
That's what I'm thinking.
Okay. Because when I first read the problem, I thought they dropped one barometer and each student calculated it differently. But I think there were two drops.
And barometers are not that cheap. I mean, the cheapest one online I can find is about $13.99. I'm assuming it's not this digital barometer, but even so.
Was it like safety reasons? Like no one's ever been killed by a falling barometer, but if they had dropped like a cinder block or like a brick, there was more risk involved?
The teacher went to the students and said, "This is my Dalvey barometer. It's something that my dad passed down to me. It's very valuable." And they took it and they chucked it off the roof.
Like they go to their science teacher, "Can we borrow a barometer for an experiment?" And they drop it off a building.
We need it for a scientific measurement. Oh, man.
Student's so proud of his kids. He comes back with the pieces of barometer left. Thank you.
Well, we got this figured out. All right. Thanks, Matt.